All right, good morning. So today we're going to talk about 14.3, which is using polar coordinates and how polar coordinates can help us to evaluate integrals, double integrals especially, that make things a lot easier. Okay, so just a refresher what polar coordinates are. Your x is equal to r times cosine theta. Your y is equal to r sine theta. And then you can show that x squared plus y squared is equal to r squared. Okay, and then you also have tangent of your angle is the y over the x, which means theta, you got theta by itself, would be tan inverse of y over x. Okay. Now, why would you use polar coordinates in a double integral? Let's think about a simple example. Let's think about if I had a circle, the radius of 1, and then a circle with the radius of 3. And I asked you, so this is a circle radius 1, circle radius of 3, and I asked you to find the area in between these two. Okay. Now, you could do it geometrically. The area in between would be the area of the outer circle, which is pi times r squared. Pi times 3 squared, 9 pi, minus pi times r squared for the inside circle. Just subtract out that donut hole in the middle, pi times 1 squared, so pi, and you get 8 pi. Okay. Now, if I asked you to find that same area, yes, we could find it using geometry. But if I asked you to find it using a double integral of dA, so we're adding up all the tiny areas, each tiny little area in here. So far, what we know, if we're using regular x and y coordinates, this dA is made up of a tiny dx and a tiny dy. Conveniently, dA is a rectangle. So we take length times width, dx times dy. So we could call this double integral of dx dy or dy dx. But then if you think about the limits of integration, that's not going to be too convenient. First of all, we're going to have to split this up into different regions. Maybe this region here. And for this interval on x, we have to go from this y to this y. And then from here to here, I suppose we could go this y to this y. We could double that because there's symmetry, and then we could go this y to this y or use symmetry. But still, it's kind of a pain in the neck to split that up. It'd be much easier, instead of dy dx, if we could use dr d theta, because we know that r goes from 1 to 3, and theta goes from 0 to 2 pi. So wouldn't that be nice? So now, does that mean we could just call dA dr d theta? Can I replace each of these rectangles with a dr times a d theta? No, it doesn't quite work that way. If you think about a polar coordinates, let's say I've got a function, just any function that looks maybe like this, and another function that looks like this, g1 and g2. And let's say I want to find the area between these two curves, but I'm going to go from this theta value up to this theta value. Okay, so this would be my first theta 1. And then this from here to here would be theta 2. You want to find this region in between. Okay, but now we've got to split that up. So anytime you use polar coordinates, we're also going to be thinking about different r values. So we've also got to think about basically radii of circles. And imagine these were infinitely close together. Whatever this region is in between these two curves, then we can draw different, segments here, or rays coming out with different angles. And each one, basically what we want to do is we add up each of these regions. Each one of these things is now our new dA. That region looks like, I'll just draw it out here. Okay. When these are infinitely small, we can approximate, or when these are infinitely small, we can say that the area of each one of these little dAs is equal to length times width, because it will become, as these become infinitely small, they'll be closer and closer to rectangles. Okay. When they're infinitely small, they will be rectangles. So we need to find this length and this width. Well, this right here, this tiny change from here to here is a dr. That's a tiny change in r, which is a length. Now this right here is actually a d theta, but d theta is not a length. That's an angle, okay? So if you remember the formula for arc length, how do we take an angle and turn it into a length? Well, in polar coordinates, our arc length was r times theta. And if this theta from here to here is your change in theta, and then we want to find the arc length of this thing or the arc length of this thing's going to be equal to r theta. And since the theta is a d theta, it's going to be r d theta. Now you might think this one's bigger than this one, but when these become infinitely small, it really doesn't matter. It's almost like a Riemann sum. It doesn't matter if you take the right endpoint or the left endpoint. When they're infinitely small, they're so close together, or they're infinitely close together that it doesn't matter. So the area of each of these, that dA is not just dr d theta, it's actually r dr times, or r d theta times dr, length times width. And this, since we need it to be an arc length, is going to be r d theta. And this is a length already. It's a tiny change in r. So the dA is r d theta. Okay? So the significance of that, when we take this interval and we want to change that dy dx into a dr d theta, it has to turn into r times dr d theta. Or the dx dy will always turn into r dr d theta. Okay. So now r goes from 1 to 3. Theta goes from 0 to 2 pi. And we can see if we in fact get the same answer we got up here, which was 8 pi. Okay, so let's do the inside integral. Integrating r, which is r squared over 2 from 1 to 3. And we get 9 over 2 minus 1 over 2. Or 8 over 2, which is 4. Now we integrate from 0 to 2 pi of 4 d theta. The antiderivative of 4 is 4 theta from 0 to 2 pi, and we do in fact get 8 pi. Okay. Now, obviously, these aren't always going to be this shape, so we can look at other examples that still could be conducive to using polar coordinates. But I want to go to example 2. So this one that we just did here, there was no integrand here. There was no function, f of x, y here. So for the next one, we're going to do example 2 on page 992. And example 2 says we actually have a ring, a region that looks a lot similar to the one that we just did. Okay, so you've got a circle with a radius of 1, which is x squared plus y squared is equal to 1. And then you've got a circle with a radius of rad 5. X squared plus y squared equals 5. So the radius would be rad 5, which is a little more than 2. So I'll just put it above here. But now we're not finding the area. We're still going to find the region, where our region is the region in between these two. But what we're going to do is find the double integral of a function. Our function is x squared plus y times your dA. So x squared plus y dy dx. Okay. From the shape of this region, that's pretty clear. You're probably going to want to use polar coordinates. So x squared, remember x is r cosine theta. So this x squared becomes r squared cosine squared theta plus your y, which is r sine theta. And then the dx dy becomes r dr d theta. Okay, this r, let's distribute that into these two terms. We have double integral of r cubed cosine squared theta plus r squared sine theta dr d theta. R is going to go from 1 to rad 5. Theta is going to go from 0 to 2 pi. Now we can integrate. We'll integrate the inside integral first. with respect to r, so we get r to the fourth over 4 cosine squared theta plus r cubed over 3 sine theta, and r is going from 1 to rad 5. All right, and substituting in our limits of integration, rad 5 to the fourth gives me 25 over 4 cosine squared theta plus, that gives me 5 rad 5 over 3 sine theta minus, plug in the 1, get 1/4 cosine squared theta plus 1/3 sine theta. Running out of space a little bit. Okay, let's simplify this minus this gives me 25/4 minus 1/4, 24/4, 6 cosine squared theta. And then I've got this minus this, so plus, I could factor out the sine theta. And I'm left with 5 rad 5 minus 1 over 3. I remember this is all inside of my first integral. So now I'm integrate this with respect to theta, 0 to 2 pi. Integrating cosine squared theta, remember that comes from the identity for cosine of 2 theta, which is cosine squared theta minus sine squared theta, or 2 cosine squared theta minus 1. Getting cosine squared theta by itself, I get cosine of 2 theta plus 1, and then all over 2. I've got 6 cosine squared theta, so 6 cosine squared theta is going to equal 6 times this, so 3 cosine 2 theta plus 6 over 2, 3. Okay, so instead of integrating this, I'm going to integrate 3 cosine 2 theta plus 3 plus sine theta times 5 rad 5 minus 1 over 3 d theta from 0 to 2 pi. Antiderivative of this is going to be 3 over 2 sine of 2 theta. When you take the derivative of this, you're going to multiply by a 2, so antiderivative, you'll divide by a 2, plus 3 theta, plus this, the antiderivative of sine is negative cosine. That's going to become minus cosine theta times your constant, 5 rad 5 minus 1 over 3. Derivative of negative cosine will be positive sine. We're evaluating from 0 to 2 pi. So I've got, let's plug in the 2 pi. 3/2 sine of 2 times 2 pi, so 4 pi, sine of 4 pi is 0, minus 3 times 2 pi. Not minus, plus 3 times 2 pi plus 6 pi minus cosine of 2 pi, so that's minus 1 times 5 rad 5 minus 1 over 3 minus, and let's plug in the zeros, plug in a 0 there, we get 0 plus 0 minus cosine of 0 is 1, so minus 1 times 5 rad 5 minus 1 over 3. Okay, so we get a 6 pi. This minus 1 times all this, and then minus a negative, that all cancels out, and we just simply get 6 pi for our answer, okay, for our integral. Okay, I'm going to stop there. Go ahead and work on the homework problems, the problems from that are assigned on the assignment sheet for today. Thank you all for watching. I will see you soon.